Tonight, the solar system holds its breath. 3I/Atlas, the third confirmed interstellar visitor, is about to fly past Mars at a mere 0.9 astronomical units, while every Martian orbiter strives to uncover its secrets. But this is not just another comet. The blazing emerald coma of the object, its unstable microaccelerations, and carbon dioxide-rich chemical composition have already broken all the rules of cometary science. Earth's instruments are about to lose contact, leaving only a few Martian probes between us and the truth. Is the 3N/Atlas a strange comet or something artificial redefining the concept of alien? When the countdown reaches 0, the hints, fragmentation, unnatural impulses, spectral anomalies, could change everything we think about visitors from the stars. Will the coming hours reveal the extraordinary or confirm that science still holds the final word? 6 hours. That is how long the window lasts before the visibility of the 3N/Atlas disappears behind the sun. At a distance of 0.19 astronomical units from Mars, approximately 28 million kilometers, an interstellar visitor races past the red planet at the moment when Earth's instruments shut down. This disconnection is not a technical failure or a planning mistake. It is geometry. For a brief moment, Mars becomes the only vantage point in the solar system. All major spacecraft in orbit, such as MAVEN, Mars Express, and ExoMars TGO, switch to high-frequency observation mode, with their teams conducting prescribed drills and improvising on the fly. In the MAVEN Control Center, the so-called redshift takes the initiative. These are operators prepared for unforeseen circumstances. These people work with decision algorithms for every possible anomaly. In the hours before the shutdown, they rehearse quick switches between standard scientific mode and high-sensitivity spectroscopy mode, preparing to change course if a sudden alert about a flare or debris appears on the screens. Prepared configurations are loaded, cross-checked with the TGO staff and Mars Express. Each team is recorded. Every data packet is backed up. There is no room for a single point of failure while the rest of the solar system remains in darkness. The schedule is relentless. Mars Express will take wide-angle shots every few minutes, overlaying exposures to capture even the faintest signs of fragmentation or course changes. The TGO spectrometers investigate the coma in search of spectral lines that should not be present. Particles and magnetometers of MAVEN monitor ionospheric fluctuations, hinting at unnatural interactions. The energy and telemetry resources of each spacecraft are pushed to the limit, and observation slots are coordinated down to the minute. If there is a threat of debris, Mars Express is ready to switch to safe observation mode, sacrificing data for survival. The cancellation threshold is set just 30% above the last measured peak density. The time of Earth's shutdown is not just a gap in communication. It is a test of all planetary scientific equipment. The coalition of red hours functions as a central hub, transmitting commands and data through narrow communication windows, prioritizing tool status, and coordinating actions with ground assets like Perseverance and Geron. In the control rooms, clocks count down the time waiting for the comet's approach. Outside, amateur telescopes listen, anticipating the first signs of a photometric burst, ready to upload data to the global alert network. For 6 hours, the fate of the observation and the question of whether the 3I/Atlas is a cosmic anomaly or something artificial depends on the ability of a small group of orbiters and their crews. The urgency of the situation is real, and the margin of error is minimal. As the window of opportunities narrows, every second becomes a potential turning point. Since its first discovery, a series of inexplicable signals has followed the Atlas. The first hints came from an amateur telescope in Pune, India, where a citizen astronomer named Prayaru noticed a recurring pulse in the light curve, which brightly manifested and then faded with a rhythm that defied explanation in cometary guides. Her post attracted attention, but the oddities only multiplied when professional observatories joined the observations. Photometric data shows that the brightness of the object sharply increased at intervals too regular for a random gas ejection. Impulses, divided by nearly identical intervals, contradict the random bursts typical of cometary activity. Each burst starts abruptly and fades smoothly, as if controlled by an invisible hand. Even as the object approached the sun, the periodicity remained clear, undimmed by distance or sunlight. Spectroscopy brought a second surprise. Instead of the usual lines of water vapor, the dominant signal in each spectrum turned out to be carbon dioxide. The ratio of carbon dioxide to water exceeded 8:1, which is several times higher than that of the most volatile comets. This chemical trace is so rare that laboratory models struggle to reproduce it. Alongside carbon dioxide, the coma glows an emerald green, peaking at 516 nanometers. This color is consistent across all instruments and confirmed by both ground-based and orbital spectrographs. Ordinary candidates, such as C2 bands and carbon monoxide emissions, cannot explain either the intensity or stability of this hue. The emission lines of nickel, especially at 337 and 380 nanometers, exceed those of iron by 4 times or more, which is contrary to what is observed in all known comets in the solar system. Images and polarimetry add another layer of information. The green light of the comet corresponds to deep negative polarization, more characteristic of certain asteroids than icy wanderers. The dust tails show grains, large and slow compared to typical cometary dust, with trajectories that are difficult to model. These grains drift along a wide, lazy arc, as if released by a mechanism that distributes mass in measured portions rather than chaotic streams. Astrometric tracking, in turn, captures microaccelerations, tiny course corrections that do not match any known gas emission profile. Each fluctuation coincides with a pulse of light, indicating a connection between light and movement. No anomaly exists in isolation. Together, they paint a portrait of an object that defies simple categories. Each dataset, photometry, spectroscopy, astrometry, adds to the growing dossier of mysteries. Evidence is gathered, waiting for an explanation that will unify all the facts. Most planetary scientists began with the simplest tools, physics and chemistry. 4 main hypotheses, each based on established models, were tested against the growing dossier of anomalies of the 31st Atlas. The first hypothesis points to chemistry formed in deep cold. In this context, the 31st Atlas formed far from any star, where water freezes, and carbon dioxide, carbon monoxide, and even rarer ices dominate. Comments from a strange cloud hinted at such chemistry, but none showed such an extreme ratio of carbon dioxide to water, exceeding 8:1. Nevertheless, it is claimed that interstellar space is vast, while our catalog is small. A single eruption can change the understanding of comet chemistry. The second model addresses the structure. Volatile pockets, deep reservoirs of trapped gases, can erupt when sunlight penetrates the crust. These pockets, if unevenly distributed, can explain rhythmic brightness pulses. Laboratory simulations show that even small temperature differences can cause sudden bursts, sometimes recurring if the layers are stratified. Regularity, though rare, is not impossible in a body shaped by billions of years of cosmic erosion. The dynamics of dust offer a third explanation. The emerald light of the coma and the presence of large, slowly moving particles may result from an unusual composition of dust or size distribution. The solar wind and weak magnetic field of Mars can form a tail, deflecting charged particles into wide arcs. Comet tail models show that under certain geometries, heavy particles lag behind, drifting in lazy arcs that mimic measured bursts. Negative polarization, more characteristic of asteroids, may hint at compact, carbon-rich particles rather than icy fluff. Finally, some point to the limits of the models themselves. Considering only the 2 previous interstellar visitors, each new arrival tests the limits of the simulation. Micro-accelerations and synchronized impulses can reflect physics not yet encoded in our software, subtle interactions between sunlight, volatile emissions, and rotational motion. In this light, anomalies are not evidence of intent, but rather a reminder of how much remains unexplored. For every mystery, the scientific community demands to exhaust all natural explanations before considering something more exotic. For 6 hours, Mars becomes the only observatory of the solar system. 3 orbital spacecraft, MAVEN, Mars Express, and ExoMars Trace Gas Orbiter, form the basis of the chain of evidence. Each of them is equipped with a unique set of tools, each designed to capture different characteristics of the passage of the 31st Atlas. The imaging MAVEN ultraviolet spectrograph, tuned to weak emissions, scans the sky for ultraviolet traces in the comet's tail, especially signs of fragmentation or sharp outbursts. His particle counters and magnetometers, operating at maximum frequency, track fluctuations in the Martian ionosphere. A sudden surge of charged particles or a change in the magnetic field may indicate that some factors beyond natural chemistry are at play. If dust or plasma from the comet interacts with the atmosphere, MAVEN's sensors will be the first to detect this disturbance. Mars Express, with its visual camera and spectrometer for covert observation, focuses on direct imaging. Broadband exposures capture the cometary cloud, searching for evidence of its decay or shape change. A spectrometer scanning from ultraviolet to infrared radiation searches for spectral lines that should not be present. Unexpected emissions, or missing water vapor. His plasma analyzer Aspera 3 tracks energetic ions that may indicate unusual interactions between the comet and the Martian environment. The NOMAD and ACS spectrometers of the ExoMars TGO are investigating a cloud in search of trace gases, hunting for isotopic ratios or molecular signatures that contradict the norms of the solar system. KSSIS, a high-resolution imager, attempts to capture the events of fragmentation or dust ejections in the process. Data from each instrument is recorded with precise timing and cross-verified in real time among teams. On the surface, the Mars rovers Perseverance and Zhurong listen for indirect signs: unusual dust emissions, changes in the atmosphere, even auroras on the horizon. Their ecological sensors and cameras provide an additional layer of evidence, though with less sensitivity than orbital devices. The checklist is clear: patterns of fragmentation, trajectory changes after a surge, spectral or radiation lines that defy explanation, isotopic ratios outside solar norms, and any signs of artificial synchronization in impulses or accelerations. Each anomaly recorded by one device must be confirmed by another. A single reading is not enough. Only matching evidence from multiple instruments and perspectives can move the situation from the realm of the unusual to the truly unprecedented. Every unit of data coming from Mars goes through multiple checks before entering the scientific registry. The first stop is duplication. Each data packet transmitted from orbital stations is duplicated, time-stamped, and recorded by independent ground stations on both sides of the Atlantic. This system protects against solar interference, transmission errors, and the rare but real risk of data corruption during a blackout. Telemetry delays, sometimes reaching several hours, as signals pass through relay satellites and deep space communication antennas, add another level of uncertainty. The mission teams prioritize packets with anomalies, those marked as possible fragmentations, spectral anomalies, or sharp trajectory changes, directing them through rapid cross-checking procedures. No single sensor or command can independently confirm an alarm signal. Each event related to the candidates is verified by at least 2 instruments, and raw data is published in open archives as bandwidth allows. The protocols of the data storage chain go beyond simple numbers. If the orbital apparatus detects a particle of dust or a fragment of ice, planetary protection specialists come into play. These experts strictly adhere to sample handling rules. All samples are sealed, receive barcodes, and are registered with digital hashes, requiring approval from both NASA and JAXA before analysis begins. The goal is clear: to ensure a clear origin. Any organic signature found in Martian regolith or atmosphere after the flyby must be traced. Future missions to discover life depend on what came from the 3I/Atlas and what belongs to Mars. Even metadata such as time, location, and instrument calibration is recorded in tamper-proof logs, ensuring the ability to audit every unusual reading for years. Outside the control rooms, a parallel network activates. Astronomy enthusiasts using their telescopes in Pune or robotic telescopes in Arizona upload photometry and astronomical data to shared databases. The first public alert about a photometric surge may come from a citizen scientist, but professional teams analyze these uploads in real time. Only after confirmation from multiple agency instruments are official statements released, urging patience and caution. Extraordinary claims require extraordinary evidence. Communication plans, prepared in advance for each scenario, emphasize transparency without sensationalism. The public channel is wide open, but every step is aimed at building trust, reserving, verifying, and creating a chain of custody that serves to issue a verdict the whole world can believe in. In the control room with red lighting, the matrix of decisions is at the center of every discussion. 3 branches: conservative, dangerous, and extraordinary determine the possible verdicts for the 3I/Atlases while data flows in from Mars. The conservative path is maintained if each anomaly can be attributed to rare but natural comet behavior. Explosions in unstable areas occur sequentially. Dust particles have unusual chemistry, and micro-movements fit within the limits of known physics. The decision becomes dangerous if fragmentation or debris clouds cross critical thresholds. A mass loss above 10% or unpredictable course changes threatening Mars's orbital devices. In this case, the priority becomes the safety of tools and data processing, rather than scientific research. An extraordinary branch is highlighted separately. She demands at least 2 independent, statistically significant anomalies of synchronized impulses corresponding to micro-movements or spectral lines that do not fit known chemical models, confirmed by different teams and instruments. No single signal, however strange, is sufficient. The rule is simple: Only matching evidence can open the door to engineering possibilities. Every operator understands how high the stakes are. In these hours, the matrix is not just a table, it is a guide to action in planetary science. New protocols require that each batch of data obtained during the interstellar flyby quickly ascends the publication ladder, becoming available within hours rather than months. The era when comet data was kept classified has ended. NASA, the European Space Agency, and the Japan Aerospace Exploration Agency approved the creation of mirrored archives where raw and annotated data is sent to open servers immediately after its integrity is confirmed by ground stations. Automated systems identify anomalies for immediate analysis, while calibration notes accompany numerical data. For teams working with Mars orbiters, emergency procedures now include compressed, high-frequency transmissions during any temporal events, followed by full spectrum and image dumps. Citizen science has ceased to be secondary. Registered amateur networks from Pune to Patagonia upload photometry and astrometry directly into verified data streams. Machine learning algorithms sort, match, and queue these uploads for professional processing, ensuring that the first signal, sometimes received from a home observatory, can attract official attention within minutes.